Today's topic, joint probability mass function. This kind of function, probability function, describes the probabilities of two random variables. Well, actually, possibly more than that, but for the moment, we only work with two. Let's have a look at an example. The function fxy is a joint probability distribution or just a probability mass function. For the discrete random variables, the mass function really works for the discrete random variables. If it's continuous, we would have a joint probability density function. All right, so fx is a joint PMF. The discrete random variables xy if, first of all, the function itself is non-negative, and the sum of fxy for all xy is 1, so f of everything, the probability of everything ought to be 1. And the meaning of fxy is the probability that x equaling little x and y equaling little y. You can treat it as an and to events intersection. Okay. If you want to find the probability of two random variables in any region A in R2, then you would just have a sum, a double sum of fxy. Here, x and y are both, xy as coordinates in A. All right, so that's the meaning of joint PMF. Let's have a look at an example. Suppose I have two coins. One coin is fair and the other coin is unfair. And I want to define two random variables, x1 to be 1 if the first coin shows the heads, and 0 if the first coin shows tails. And x2 also if the second coin shows heads and is 1, and the second coin shows tails, it's 0. These are two random variables. And we know the probability of x1 equals, the probability of x1 equals 1 equals 1/2. The first coin is fair. That equals the probability of x1 equaling 0. And I'm going to just assign the probability that x2 equaling 1 is 2/3. And the probability of x2 equals 0, so 1 minus that, 1/3. Okay, I randomly choose these numbers, just make it unfair. Now I'm going to define, oh, by the way, these two coins are tossed independently. So in the sense that these events would be independent. Later on, we're going to introduce the concept of independent random variables. So basically, we're two independent coin tosses. All right, I want to define two new random variables. Say x equals x1 plus x2, y equals y1 plus y2. Hey, that's not good. Y equals x1 minus x2. And we're looking for the joint PMF of x and y. Find the joint PMF of x and y, two random variables. For this problem, it's probably more convenient to talk about, to use a table, to list all the probabilities. This is one way of showing a joint PMF, just to use a table. Sometimes use function, and we're going to have another example shortly. All right, so let's draw a table. And here is the possible values of x, possible values of y. X is the sum of the two random variables, and the two random variables can take either 1 or 0. So add them up, you could have 2, you could have 1, you could have 0. 1 means one of the two tosses shows heads and the other shows tails. The y is difference. Y is the difference. So you could have a 0 minus 1, you have a negative 1, 1 minus 1, 0 minus 0, you get 0, and 1 minus 0, you get 1. So you have these two values, three values. All right, let's try to figure out the probabilities. So this one, that would represent the probability that x equals 2, y equals negative 1. So let me just write down what it looks like and then give the value, work with the value later on. That's what it means. Okay, probability of x equal 2, y equal negative 1. It's not straightforward to work with this event directly. We need to translate it to the events with respect to x1 and x2. That will be easier. So x equals 2. X equals 2 means what? Means both tosses would yield 2 heads, or yield heads. Right? X is capital X is the sum of the two random variables. So basically it will be equal to x1 equals 1, x equals 2, x2 equals 1. That's the same as the probability of x equal to 2. Then the difference cannot be negative 1. So y cannot be negative 1. So it cannot happen. The probability would be 0. So we put 0 here. And the probability of x1 1 1 and y equals 0. That's actually obvious. It's just it's always the same. So if x1 x2 both equal 1, then capital X equals 2 and y equals 0. What it means is that this thing, they are simply, so the probability of x equal to 2 and y equals 0, they're the same event, which is x equal to 2, which is x1 equals 1, x2 equals 1. That means both tosses would show heads, and they're independent. You have a 1/2 times 2/3, you get 1/3. This equals, they're independent. It's 1/2 times 2/3. Okay. Similarly, for this one, if x equals 2, then both are heads, then it's not possible the difference is 1. So you get 0 here. Finish the first column. Let's look at this one. This number is the probability that capital X equals 1 and capital Y equals negative 1. So that's what it means. The probability that capital X equals 1, capital Y equals negative 1. So X equaling 1, there are two possibilities. So one's heads, one's tails, right? The first one's heads, second one's tail, and then the first one's tail, the second one's heads. But Y equals negative 1, that will force the first toss to be tails. So this is really, the first one is tail, and the second one is heads. And using independence, you have half times 2/3, you get 1/3 again. We put 1/3 here. All right, next one. So you have x equaling 1 and y equals 0. That's not possible because x equals 1 and 1 has to be one has to be heads, 1 has to be tails. You don't get 0, don't get the sum to be 0. And if this one, that means x equaling 1 and y equaling 1. That means the first one is heads, the second one is tail. That's 1/6. 1/2 times 1/3. That's 1/6. And this one, when x equals 0, both are tails, so it's not possible to get the difference to be -1. And this is not possible. And this one, that really says both are tails. Both are tails. You have 1/2 times 1/3, which is 1/6. This table shows the joint PMF. Okay. And the grand total, the second part of the definition, the sum of everything should be 1, so this should be 1, and you add them up. Yes, indeed, it's 1. Okay, so this is the joint PMF. We can get it by reasoning out all the probabilities. Next, I want to introduce the concept of a marginal distribution. The marginal distribution, there are two of them if we are talking about joint PMF of x and y. So two variables, so you have two marginal distributions. Marginal distribution of x, we can use little g of x. Sometimes we have a simply mark something like that. So this x is to show it's marginal for capital X. It's the summation of the joint PMF with respect to y. So add everything, all the masses on y. And similarly, we have a marginal distribution of y. Sometimes we use this kind of notation. That's the sum of fxy for all x. All right, that's for discrete case. For continuous case, we're gonna have a different short lecture. So this is for the marginal distribution of x. So you have x2, and then you add all these numbers. These are f of 2y, so y equals -1, 0, and 1, right? So that's what means the marginal distribution of x when x equals 2. That equals the sum of all y, and you have a joint PMF. So literally just add these three numbers, you get 1/3, and add these three numbers, you get 1/2 and 1/6. Add them up, you'll get 1. Because the marginal distribution is a distribution. And here you have the marginal distribution of y. When y equals -1, you add up all these the joint PMF when y equals -1, you add up all the x's. So what I mean is that fy of -1, that equals the sum of fx -1 for add up for all x. So it's still just one term, 1/3. And similarly, you have 1/2 here and 1/6. Again, you add up to be 1. All right, so these are the marginal distribution of x, marginal distribution of y. All right, so that's this concept. Let's move on to another new concept called conditional distribution. Conditional distribution. The definition of conditional distribution is simply the joint distribution divided by the marginal. Okay, that's what it says. So f of y given x is the joint distribution divided by the marginal of x, and the other way around is the marginal divided by the joint distribution divided by the marginal of y. Okay. So let's look at this example. So what is the conditional distribution of there are two different notations, okay? Some people use this notation. So it's a conditional distribution of x and y, this kind of thing. All right. So let's say the conditional distribution of x given y equaling say 0. Okay, that's a little bit more interesting. What this thing is? It's a distribution of x, but given y equals 0. All right, so it would be this joint joint probability divided by the marginal probability, which is 1/2. So it would be 2/3. So f(x) given y equals 0, x is 2, y equals 0, that is 1/6. And f(x) y equals 0, and you have 0. That's 2/3. And 0, that would be 1/3. It's 1/6 divided by 1/2. Okay. So what is this divided by this number? Okay, so these two numbers form a distribution, conditional distribution of x given y equals 0. And when x equals 2, you get 2/3. When x equals 0, you get 1/3. Right, so it's a little bit tedious to list all the conditional distributions. All right, so this is a let's work with another one. I think it should be good. So it's y given x equals 2. So you're gonna divide these numbers by 1/3 here. Obviously, this only one number which is not 0. So we have 2y. Okay, so this is a distribution. It's a function, but the only value that is 0 is non-zero is when y equals 0. So you have a 2, 0 equals 1. Okay, given x equals 2, then both tosses show heads, add them up, you get 1. Then y has to be 0. So it's deterministic, sort of, given the information that the sum is 2. Okay, so that's the three topics we cover. One is the joint PMF, the second one is marginal PMF, and the third one is conditional PMF. Let's have a look at another example, which is given by a function. It has a form of function instead of a table. So let's look at that. Okay, now this one. So determine the values of C. First of all, determine the value of C so that the following function represents joint probability distributions of G. A bunch of no S here. Determine the value of C so that the following function represents the joint probability distribution of the random variables x, y. It's from a problem which has several smaller problems. That's why you have all these values and distributions. Anyway, we have this joint PMF fxy equals cxy. And x takes value 1, 2, 3, y takes value 1, 2, 3. One way of working with this is just to draw the table like what we did earlier, but then I'll give you a different way of looking at it. Just use the double sum, but some people don't feel comfortable with double sum. That's all right. 1, 2, 3, y 1, 2, 3. cxy. So C, you have a 2C, you have a 3C. And here you have a 2C, you have 4C, you have a 6C. Okay, remember you multiply x value and y, x value and y value, and multiply by C. Okay, you have CXY. And then you have 3C, you have a 6C, and 9C. Add together, you have a 36C, but it has to be 1, so we get C to be 1 out of 36. And now you have a 136 here, and then you have a 2 out of 136 and so forth. But anyway, C got 136. That's one way of doing that. It's a little bit tedious. Another way, you simply add everything. Double sum of fxy for all x from 1 to 3, y from 1 to 3, add them up, you get 1. So you take a sum, you plug in cxy, x equaling 1 to 3, y from 1 to 3. When you take the sum with respect to x, you can treat y as a constant. So you can do this, 3y, and the summation of x from 1 to 3, and y from 1 to 3. And this one, 1 plus 2 plus 3, which is 6. So you have a 6cy, and then y from 1 to 3, and then move out 6c, sum of y from 1 to 3, get 6 again, 36c equals 1, c equals 136. Okay, so that's the joint PMF fxy equals 1 out of 36 x times y, xy equals 1 to 3. Okay. Now let's work with marginal distribution. There are two marginal distributions, right? Let's do x, and that is the sum of a joint PMF. Work with all y's, y from 1 to 3. So you get 1 over 36. X, the constants with respect to y, so move it out, move it out, and you get 1 out of 6 times x. This is 6 divided by 36. You 1 out of 6 times x. And similarly, fy of little x, that would be the summation of all x fxy and you're adding x, so cy, so 1 out of the 36y times the sum of all x from 1 to 3, which is 6. So you get that, they're the same. So these are two marginal distributions. And the conditional distribution, there are two of them, conditional distribution. Fx given y, that would be the joint one. 1 out of 36xy over the marginal of y, so 1 over 6y. That would be 1 over 6x. They are the same. There's a property that describes these two, this kind of result. And similarly, y given x, xy, you have the joint 1 over 36xy divided by 1 out of 6x, and you get 1 over 6y. Again, x is 1, 2, 3, y is 1, 2, 3. Okay, so that's an example, simple example for this kind of functions.